Multidimensional scaling. Let us say for n points, we are given the distance between pairs of points dij for all I and j starting from 1 to 3 or n, all those pairs. We do not know the exact coordinates of the points, their dimensionality, or how the distance are calculated. Multidimensional scaling, MDS, is the method for placing these points in a low, for example, two-dimensional space such that the Euclidean distance between them there is as close as possible to Dij, the given distances in the original space. Thus, it requires a projection from some unknown dimensional space to, for example, 2 dimensions. In the archetypical example of multidimensional scaling, we take the road travel distances between cities, and after applying MDS, we get an approximation to the map. The map is distorted such that in parts of the country with the geographical obstacles like mountains and lakes where the road travel distance deviates much from the direct bird flight path Euclidean distance, the map is stretched out to accommodate longer distances, see figure 6.6. The map is centered on the region, but the solution is still not unique. We can get any rotated or mirror image version. MDS can be used for dimensionality reduction by calculating pairwise Euclidean distances in the d-dimensional X space and giving this as input to MDS, which then projects it to a lower dimensional space so as to preserve these distances. Let's say that we have a sample X equals to the set X to the transpose, where t is starting from 1 to n as usual, where x to the d is in r to the d, x to the t is in r to the d. And for 2 points r and s, the squared Euclidean distance between them is drs to the square is equal to the square of the distance between x to the r minus x to the s, that is, by definition, equals to the summations of sigma of xj to the r minus xj to the s, then to the square, summing for all j starting from 1 to d. And if we separate all these terms by the expansion of expanding these terms inside of the square, there will be the following three terms. The summations of xj to the r to the square, summing with j starting from 1 to d, minus 2 times the same summation for the same range of j of the term, xj to the r times xj to the s, plus the summations of the same range of j of the term, xj to the s, then to the square. If we replace it by the new terms defined below, there will be BRR plus BSS minus 2BRS, where BRS is defined as BRS equals to the summations of XJR times XJS. Again, the J is starting from 1 to D. To constrain the solution, we center the data at the region and assume that the summations of xj to the t is equals to 0, where the summation is summing for all t starting from 1 to n, and it's for all j starting from 1 to 3 until d. Then summing up equation 6.24 on Rs and both Rs, and defining t equals to the summations of btt, where the summation summing for t starting from 1 to n is equals to the doubling summation, where the outer summation is summing for all t, the inner summation is summing for all j of the term, xj to the t, then to the square. And we get the following. The summations of drs to the square summing for all r is equals to t plus n times bss. The second term, the summations of drs to the square summing for all s is equals to n times brr plus t. The third doubling summation summing for all r and all s of the term drs to the square is equals to 2 times n times t. When we define the d dot s to the square is equals to 1 over n times the summations of drs to the square summing for all r, and the dr dot to the square is equals to 1 over n times the summations of drs to the square for all summing for all s, and d dot dot square is equals to 1 over n square, summing for all doubling summation summing for all r and all s of the term drs to the square. And using equation 6.24, we get BRS equals to, we just replace the terms, equals to 1/2 of dr dot to the square plus d dot s to the square minus d dot dot to the square minus drs to the square. Having now calculated the BRS and knowing that B equals to x times x transpose as defined in equation 6.25, we look for an approximation. We know from the spectral decomposition that x equals to c times d to the 1/2 can be used as an approximation for x, where C is the matrix whose columns are the eigenvectors of B and d to the 1/2 is a diagonal matrix with the square roots of the eigenvalues on the diagonals. Looking at the eigenvalues of B, we decide on the dimensionality k lower than d and n as we did in the PCA and FA. Let us say Cj are the eigenvectors with lambda j as the corresponding eigenvalues. Note that Cj is n-dimensional. Then we get the new dimensions as Cj to the t is equal to the square root of lambda j times Cj to the t, where j is starting from 1 until k, and t is counting from 1 until n. That is, the new coordinates of this instance t are given by the tth elements of the eigenvectors Cj, j starting from 1 until k after normalization. It has been shown in 1980s by Chetfield and Collins that the eigenvalues of x transpose n by n are the same as those of x transpose times x d by d, and eigenvectors are related by a simple linear transformation. This shows that PCA does the same work with MDS and does it more cheaply. PCA done on the correlation matrix rather than the covariance matrix equals doing MDS with the standardized Euclidean distances where each variable has unit variance. In the general case, we wanted to find a mapping z equals to g of x conditioning on theta, where z is in r to the k, x is in r to the d, and g of x conditioning on theta is the mapping function from d to k dimensions defined up to a set of parameters theta. Classical MDS we discussed previously corresponds to a linear transformation. Z equals to g of x conditioning on w, which is equals to w transpose times x. But in the general case, a nonlinear mapping can also be used. This is called the Salmon mapping. The normalized error in mapping is called the Salmon stress, and is defined as expectations of theta conditioning on x is equals to the summing for all rs of the term r z to the r minus z to the s, then minus x to the r minus x to the s. Okay, the following thing to the square divided by the following term, the square of x to the r minus x to the s, which by the definition of what we defined of z as the g of x conditioning on w, that will be equals to sigma for summing for all rs of the term g of x to the r conditioning on theta minus g of x to the s conditioning on theta, then minus x to the r minus x to the s. After that, we take the square divided by x to the r minus x to the s, then to the square. One can use any regression method for g of that conditioning on theta and estimate theta to minimize the stress on the training data x. If g dot is nonlinear in x, this will then correspond to a nonlinear dimensionality reduction. In the case of classification, one can include class information in the distance. See Web 1999 as drs prime equals to 1 minus alpha times drs plus alpha times CRS, where CRS is the distance between the classes x to the r and x to the s belong to. This interclass distance should be supplied subjectively, and alpha is optimized using cross-validation.